Alright, so in the last video we talked about what line integrals were, and we talked about how to derive some important results simply by using trigonometry. And then we arrived at the following expression. So we found that in order to integrate a function of several variables with respect to just an arc length on a curve, all we need to do is just represent each of those variables as a function of a single unique parameter t, and that has to be a parameter that they all have in common. And then the parameterization of that curve C is going to depend on what kind of curve we have. So the three most common ones that we encounter in practice are straight line segments between 2 points. So we know that we're going to have the following kind of representation in vector form. The second one is going to be a circular arc of radius r. So we can represent it using polar coordinates in this form, and we know how to find the limits of integration for those. And then the final case is where you just have a function y explicitly as a function of x, and then the limits of integration are just given by the limits on x. So that one is the simplest of those cases. Now, before we actually move into an example, what I wanted to do was basically just talk a little bit about what we're actually calculating when we calculate a line integral. So I know I probably should have done this in the last video, but I wanted to give you more insight here. So the idea is we're taking a function of several variables. So let's suppose that we have a set of three axes here, x, y, and z. So a function of two variables is going to be a surface. So it is going to look something like that. Now the interesting thing is that, say you take a curve in 2 dimensions. So you take a curve that goes like this between 2 points. And now what you're doing with this is you're taking the values of the function essentially at those points that correspond to the curve C. So essentially you're integrating, you're summing up the total height, or basically just a bunch of rectangles that span all across that curve, but they lie beneath that actual surface. So basically you're going to be doing something like this. So line integral, in the case of the two-dimensional function, is essentially just a wall. You know that in general, if you were integrating this using a double integral, you would get a volume underneath that surface. In the case of a line integral, you're getting just a wall of infinitesimal width, but basically that it spans all along that curve C between the 2 points. So this is basically what you're doing when you calculate a line integral. And it has some important physical applications that we'll discuss a little bit later on. So now let's start with a simple example. Let's have the following function, ds, and let's define a curve C. So let's say that C is just an upper half circle. So the equation of the curve is going to be this one. And we're going to confine that to the upper half of that plane. So we're going to have y equal or greater than 0. So the first thing we do is we draw a region or a curve essentially. So we have a circle or semicircle of radius 1. And it is centered at the origin. So it is going to go around like this. And usually when we talk about line integrals, we specify a specific direction in which we're integrating. So let's say that we're going anti-clockwise here. So we're integrating this direction. Now what's going to happen is, well, we need to find a suitable parameterization for this. Now, if we go back to our little list of different parameterizations, we know that polar coordinates is probably the most suitable for this case because we have a half circle there. So let's say we write x as a function of t. So t is just a parameter. In this case, the parameter is just the angle. The radius is constant, it's just 1. And then we're going to have cosine of t. And similarly, we're going to have y as a function of t. So this is going to be sine t. And now we need to define what the limits on t are. Well, basically the limits on t are going to be from 0 all the way to pi radians, because in this case t represents the angle. So we're starting off here and then we're rotating all the way to here, so we're covering 2 full quadrants, which gives us a rotation of pi radians. Now the next thing we need to do is, of course, obtain the element ds, and to do that we need to differentiate each of these with respect to t. So dx over dt is going to be minus sine t, and then dy over dt is going to be equal to cosine of t. So now all we need to do is we put those into ds. So ds is going to be equal to dt times the square root of d squared. So we're gonna have minus sine t squared plus cosine of t squared. And using trigonometric identities, we know that these two are going to add up to 1. So this gives us dt times the square root of 1, which is just dt. So it turns out that this arc length element in this case is just going to be dt, which is going to simplify things for us quite a lot. And the next thing is, of course, to represent this function in terms of those parameters as well. So we have a function of x and y. Now it is 2 plus x squared y, and then if we put those two parameterizations in, we're going to get the following: 2 plus cosine squared t times sine of t. And now if we put all of this information together, what we're going to do is we're going to have the integral of c for this function 2 plus x squared y ds is going to be equal to the integral. Now we introduce the limits here, so from 0 to pi of the function 2 plus cosine squared t sine t, and then we're going to multiply it by this element, which turned out to just be dt. So we're going to have this. Now we know from the theorem of integrals that we can just separate this into two. So we have 0 to pi of 2 dt plus 0 to pi of cosine squared t sine t dt. The first one is quite straightforward. We're going to get just tt evaluated from 0 to pi. And then for the second one, well, we're going to use substitution. So let u equal to cosine of t such that the derivative equals to sine t times dt. And then we find that this is actually going to turn out to be minus 1 over 3 of cosine to the power 3 t. Because you know that if you differentiate this, you're going to bring the 3 down. That cancels out with this one. This is going to become, we're going to have cosine squared t times the derivative of this, which is minus sine. So then it all reduces to this. So from 0 to pi. So let's see what this gives us. Well, here we're just going to have 2 pi. We're going to have minus 1 over 3 of cosine to the power of 3. So cosine of pi is just going to be minus 1. So we're going to have minus 1 to the power of 3. That's still minus 1. And then we're going to have to... Actually, this is going to be positive because we're going to have minus here. We put 0 in there, and then this is just going to be, let me see, it is going to be negative as well. So it got a little bit confusing. Actually, it's just going to be plus. Yeah, what am I talking about? Yeah, so make sure you write it down so you actually know what you're doing. So this is just going to be 1. So we have plus 1/3 plus 1/3. That becomes 2 pi plus 2/3. And this is the final answer. So in this case, if you were to take this function, so let's say x, y, and z, and now what you have here is you have this semicircle of radius 1, and then we have this function here, which is just a surface. Let's say the surface looks a little bit like that. Then what the line integral here is telling you is that you're finding out what the value of this area that extends vertically upwards is going to be. So this whole, it's kind of like a wall essentially. So this is the value of the line integral, and it turns out to be 2 pi plus 2/3. And that's it. That's how you find the line integral. So you notice that the first step was obviously identifying a suitable parameterization. Then we found the arc the element of integration ds based on dt and based on those two derivatives. And then we simply subbed in the limits of integration and all the other functions, and we just found that as a single integral. And in the next video, we're going to continue with some more examples on this.